Okay, this is going to be chapter 4.3 circuits. Question number 1 here. The diagram represents 4 copper wires. Which wire has the greatest resistance? From here, you're supposed to recall the formula that resistance is directly proportional to length and inversely proportional to area. Meaning to say, the longer the length, the greater the resistance. The smaller the cross-sectional area, the greater the resistance as well. So looking at this part here, this one has the greatest length and the smallest cross-sectional area. So C is definitely supposed to be the answer here. Yeah. Then question number 2, 4 circuits are set up. In which circuit does the ammeter show the greatest reading? In order for the ammeter to show the greatest reading, I will be equals to V over R. We'll need to have the smallest resistance. Looking at the resistance here is 1 over 2 plus 1 over 3, right? Which is going to be 3 over 6 plus 2 over 6 here, which will be 5 over 6. Which will be 6 over 5 because it's 1 over, this is only 1 over RT, right? The total resistance here is 1.2 ohms. Here the resistance, since this diode blocks the current can only flow here. So there's a total of 3 ohms here. This current is unable to flow through any of the resistors, so there's a 0 ohm here. And the current is able to flow through here, which is obviously the 2 ohms, right? So looking at these 4, C, even though has the smallest resistor, it's not going to have any current because it has 0 resistance. So A is the only logical answer here. Next, the diagram shows an electric circuit. The light falling on the light-dependent resistor increases. Light-dependent resistor increases means to say the resistance is going to drop. What happens to the resistors of the LDR? The current in the fixed resistor and the reading in the voltmeter. So obviously, since the light intensity increases, the resistance of the light-dependent resistor is going to drop. Since the resistance drops, the current is obviously going to increase. And from there onwards, since right now the resistance here is relatively lower than the resistance here, this voltage is definitely supposed to increase. So B is the definite answer here. Right. Then moving on to question number 4, the diagram shows 2 linked circuits to control when a bell is switched on. The conditions are altered and only one pair of condition causes the bell to ring. Which pair causes the bell to ring? This is obviously a relay switch here. I want to have more current flowing here, meaning to say I want both of these resistors to be low. Since this is a light-dependent resistor, the light intensity must be high. Since this is a thermistor here, for the resistance to drop, the temperatures must be high as well. So bright light and high temperature, this is going to be your answer here. Alright, then moving on to question paper 4. Figure 8.1 shows a 12 volt power supply connected to the circuit. There's a 12 volt here. The circuit includes a lamp and a resistance wire AB. There is a resistance wire AB here of constant cross-sectional area. There is a sliding contact that can be moved between A to B. So if I'm moving between A to B here, I'm effectively adjusting how much the current needs to flow, how much of the current needs to flow through the resistance wire. Here being the minimal amount of resistance, and here being the maximum amount of resistance here, right? So keep that in mind. The rating of the lamp at normal brightness is 6 volts and 9 watts. 6 volts and 9 watts here. Calculate the current at the lamp during normal brightness. Since I already have power and voltage, I'm asked to find current. You're supposed to use the P equals to VI formula. I would be obviously P over V, which is going to be 9 divided by 6, which is going to be 1.5 amperes here. So your first question, you're supposed to get 1.5 amperes. Then the resistance of the lamp at normal brightness. Right now, if I want to find the resistance, I can use the V equals to IR formula. R will obviously be V over I, which in this case here will be 6 divided by 1.5, and I am supposed to get 4 ohms here. Right, I'm supposed to get 4 ohms here. Then from here onwards, AB is 1 meter long and has a resistance of 5 ohm. This AB is supposed to be 1 meter long. At normal scenario, it will have 5 ohms here. The lamp has normal brightness when the sliding contact is at X. The lamp will have normal brightness here when the sliding contact is at X exactly. Okay. The sliding contact is moved to B. Explain without any calculation why the lamp becomes dimmer. If the sliding contact moves to B here, what's going to happen is it means to say that my current has to flow through more of this resistance wire here, meaning to say the current will be less because the resistance in this circuit is going to be much higher. And without any calculation, you're supposed to say, the resistance of the wire at B is much higher than at X, right? Then obviously the current is decreased, right? The current in the lamp decreases. Okay, something like this, or anything logical, right? Then from here, the final question, which usually the students struggle a little bit, and they ask us to calculate the distance AX for the lamp to have normal brightness. Now, since I know that right now, this lamp here, and a normal scenario, is supposed to be 5 ohms, right? At X, this thing here will be at maximum brightness. And since this thing here already consumes 6 volts, can I assume that this part of the wire is going to be 6 volts as well? And since we already calculated that the current is supposed to be 1.5 amperes at normal working condition, then I can find the resistance here straight away already, right? I can use the V equals to IR formula. In this case here, V will be equals to IR. R will be essentially how much? 6 over 1.5, which is eventually supposed to give me 4 ohms as well. If this thing here is 4 ohms, right? Maximum length of 1 meter is equals to 5 ohms. When I want it to be 4 ohms, what length should this be here? You can calculate it using normal ratio, which is obviously going to be like 4 over 5 is equals to X over 1 here. Your X would supposedly be 0.8 meters here. Alright, so you're supposed to take all of that into consideration. You're supposed to say that since V is equals to IR, right, my R of the wire was going to be 6 volts divided by 1.5 amperes, which is going to be 4 ohms. When the wire is 1 meter, it's equals to 5 ohms. When I want it to be 4 ohms, how many meters should it be? Obviously, you're going to use like 4.5. 4 over 5 is equals to X over 1, which if you press everything in the calculator, your X would have been equivalent to 0.8 meters here. It's going to be 0.8 meters here. Okay? So just make sure you write this, 0.8 meters. Then moving on to this next part here, figure 9.1 shows a graph of current against potential difference for a filament lamp. State what happens to the resistance of the lamp as the potential difference changes from 0 to 1. From 0 to 1, you can see that this line is going to be a straight line. So obviously, the resistance is going to be constant, right? So you're supposed to mention that resistance is constant. Then from 1 volt to 8 volt, which is this next part of the line here, you can see that it's starting to tilt towards the V. And if you use back the Ohm's law formula, R is equals to V over I, right? Tilting towards V means to say the voltage increases more than your current. Obviously, your resistance is going to increase here as well. So you're supposed to say resistance increases. Okay? Then, next part here, at normal brightness, the potential difference across the lamp is at 8 volts. Calculate the normal brightness, the resistance of the lamp. If I want to find the resistance of the lamp, all I need to do is just dot all the way upwards here. And I dot all the way to here. You should be able to find that the current should be somewhere around, let me just erase all this here. 8 is going to be one straight line all the way up here, and it's going to be all the way to here, which is 0.6, 0.62, 0.64, 0.66, 0.68, 0.7, then 0.72 here, 0.72 amperes, right? So if I want to find the resistance, R will be V over I, which in this case will be 8 divided by 0.72. Right, if I put 0.72 here, press that in my calculator, 8 divided by 0.72, it's supposed to give you 11.1 ohms now. 11.1 ohms here. Right. After that, they ask you for the power of the lamp. Power is essentially VI, right? Which in this case here will be 8 times 0.72 lah. 8 times 0.72. You'll get 5.76 watts. 5.76 watts here. And this concludes the first exercise. Looking at the second exercise here, the diagram shows a circuit. You can see that the current is coming here, and then here, and here. Then the diode will only allow this current to flow here. It will be blocked here because at this junction, the resistance will be too high. No current is able to flow. When switch S is closed, which lamp lights up? Obviously, the only logical answer is going to be A here, right? Because the current is not able to flow to lamp 2's line. The circuit contains 4 ammeters and 3 resistors with different values. Which ammeter shows the largest reading? So you can see that the current is going to flow here, split here, split here, split here, and then combine back here. So without any calculation, I know for a fact that donkey is the absolute answer here. There is a current of 5 amperes in a resistor. The potential difference across the resistor is 24 volts. How much energy is transferred in a resistor in 1 meter, which is 1 minute, which is 60 seconds here. Energy is supposed to be equals to VIT. You can refer to the formula here, which is 24 times 5 times 60. Press everything into the calculator. I'm pretty sure it should be not smaller than 290, right? So obviously 7,200 joules is the only logical answer here. The lamp of a car headlight is rated at 12 volt at 50 watts. Calculate the current. You're supposed to use the P equals to VI formula. I will be equals to P over V, which is 50 divided by 12, which is going to be 4.16. You're supposed to get 4.16 amperes, correct to 3 significant figures lah. Okay. Then after that, a car is driven at night. In a journey, the total charge that passes through the 12 volt battery is 270 kilocoulombs. So it's 27000 coulombs. Calculate the electrical energy transferred. I have voltage, I have charge, and I'm looking for energy. This is essentially the EMF formula, which states that V is equals to energy over charge. For those who cannot remember, electromotive force is the amount of energy needed to drive 1 coulomb charge around the circuit. That's the definition of EMF. So in this case here, it will be E equals to V times Q lah, which is 12 times 270,000. 12 times 270,000, you'll get 3 million, which I'm going to change to the standard form, 3.24, 1, 2, 3, 4, 5, 6 times 10 to the power of 6 joules. 3.24 times 10 to the power of 6 joules here. Right. Then figure 9.1 shows current potential difference graph for resistor and a lamp. The potential difference across the lamp is 6 volts. Okay, 6 volts here, somewhere around here. Calculate the resistance of the lamp. I'm supposed to find the current. If it's 6 volts at the lamp here, the current should be somewhere around 4.4, right? 4.2, 4.0, 4.2, 4.4, 4.6, 4.8, 5, 5.2, 5.4, 5.6, 5. Yeah. So this is going to be 4.4 amperes here, right? So if you press that into your calculator, you're supposed to get R is equals to V over I, Ohm's law formula yet again, 6 divided by 4.4, 6 divided by 4.4, you're supposed to get an answer of 1.36 ohms. 1.36 ohms here, yet again correct to 3 significant figures. The lamp and the resistor are connected in parallel. They are connected in parallel to a 6 volt power supply. Calculate the current from the supply here. If it is 6 volts, all I need to do is find the current here as well. The current should be somewhere around 4, right? So it's just a matter of adding them both together, right? Yeah, it's just 4.4 plus 4 lah, which is supposed to be 8.4 amperes. Not sure why it's 2 marks here though. It's a bit odd. As long as they're connected in parallel, you're supposed to add the currents up. But no one complains about 3 marks, right? Then moving on to this next question here. The lamp and the resistor are connected in series to another power supply. The current in the circuit is 4 amperes. Calculate the total potential difference across the lamp and the resistor here. So from here, I actually need to find... Oh, actually, I'm a bit lost. What am I supposed to find here? They say the lamp and resistor are connected in series. The lamp and the resistor is connected in series. The current is going to be 4 amperes here. And 4 amperes here as well. From here, I want to find the potential difference across the lamp. I want to find the potential difference, which is the voltage lah, right? If I want the voltage, I'll need the current and the resistor. So I guess I'll have to find the resistance of each and every one of them, right? At 4 amperes, oh God, at 4 amperes, how much will the voltage be? I think I can get it from the graph as well. At 4 amperes, this thing here will have a potential difference of probably 5, 4.2, 4.4, 4.6, 4.8. The lamp will be 4.8, and at 4 amperes, this potential difference here will be 6 volts. So all I need to do, I guess, is just add them both together, right? And it's going to be like 6 plus 4.8. It's going to be 6 plus 4.8 lah. 6 plus 4.8, which is supposed to give you 10.8 volts, guys. You're supposed to get 10.8 volts here. Okay. Then, final part of this question here, figure 9.1 shows the current potential difference graph for a resistor and a lamp. The potential difference applied to the resistor is increased, so the potential difference is increased here. Tick the box that indicates the effects of the resistance of the resistor. Since it is a straight line in the current versus voltage graph, obviously the resistance is going to be constant, right? So second box is definitely ticked. The potential difference applied to the lamp is increased. The potential in the lamp is increased. Tick the box that indicates the effects on the resistance here. You can see that the graph tilts more towards the voltage part. If you look back at the formula, more voltage increase means to say the resistance is supposed to increase. And finally, the potential difference across the lamp is 6 volt. Calculate the resistance of the lamp. 6 volts here to the lamp, it's probably going to be 4.4 as well, right? Oh, this is the current, so it's 6 divided by 4.4. Then I'll have to yet again press in the calculator. We're supposed to get once again 1.36 1.36 ohms here, correct to 3 significant figures. Okay, then moving on to the final exercise here. Which electrical symbol represents a diode? Logically speaking, B is the only answer. A student sets up this circuit. What is the purpose of this circuit here? This is a thermistor. This is a alarm bell, right? To allow the lamp to be made dimmer, there's no lamp here. To amplify the sound of your voice could be possible. To light up a lamp in the dark, definitely not. This is not a lamp. To sound a bell when the temperature increases, logical. This is obviously the answer here. When the temperature increases, the resistance drops, means to say more current flows through the bell, and obviously it's gonna ring lah. Alright. Then moving on to this next part here. The diagram shows 2 voltmeters P and Q connected to a potential divider. The sliding connection at point X moves towards the top. So you can see that this sliding connector is moving towards the top here. What happens to the reading? Now, whenever you're dealing with all these potential divider questions, so you have to be careful of where the positive side of the battery is. If the positive side is here, it means to say starting from here, this is zero resistance, and going here, this is maximum resistance. So looking at Q itself, when it moves from the middle to X, the resistance maximizes, so obviously the voltage is supposed to increase. Voltage is supposed to increase. And since this P is on the other side, and it gets a minimal amount of resistance, then obviously it's supposed to decrease. So B is the answer here, guys. Then the diode is used as a rectifier. Rectification is to convert our AC into DC. What is the purpose of a rectifier? To allow current to pass in either direction, not logical. To change alternating current to direct current here. This is obviously the logical answer. Right? Then the 3 ohm resistor is connected in parallel with a 4 ohm resistor. While the resistance of these two combined is essentially 1/3 plus 1/4, which will be 12/4 plus 3/12, which is 7/12. This is equals to RT. Always remember to flip it, so it's 12 divided by 7, which is going to be 1 point something. And the logical answer here, it could be none other than C. And question 6, what is electromotive force? Like I mentioned, you can use it according to the formula. Electromotive force is the amount of energy needed to drive 1 coulomb charge around the circuit. The amount of charges that passes through a cell, the energy gain per unit charge as the this could be logical. The total amount of charge flowing through the cell, the total energy stored in the cell. No, the only one that is more logical is B, which tallies most with the equation. A piece of wire is 40 cm long and has a diameter of 2 meters. The resistance is 3 ohms. What wire of the same material has a resistance of 0.15 ohms here, which is essentially half here, right? Now, if I want to halve this, right, I could either halve the length, but I have to keep the diameter, or let's just go through each and every one of them and see what goes on now. When I halve the length here, this will be 0.15. When I halve the diameter, this actually quadruples. This actually quadruples the resistance, because this diameter has to go through the area, which is going to be pi d over 2 square, right? When you halve the diameter, because of the square component here, it actually quadruples the area. So if this was the case, right, this will cause the resistance to increase times 4, which is going to be 0.6. So this is not logical. Yet again, this one here, 0.15, and then the diameter double up, right? If it double up, it quadruple down the resistor. So this is not logical as well. From the length here, if it double up, it's actually going to become 0.6 ohm from here times 2, right? Then when the diameter double down, you're going to quadruple up the resistance, which is going to be 2.4 ohms here. So it's not logical. Here yet again is double upping the length, so it's going to be 0.6 ohm here. And then you double up the resistance, which quadruple down the resistance here, which is going to be 0.15. So logical answer is going to be donkey here. In these kind of questions, it's always good to remember that the resistance is length over area. When you double up the diameter, you actually quadruple up the area, which is going to cause the resistance to quadruple down as well. Always remember that resistance and area, they are inversely proportional to each other. Okay. Then an electric meter records 200 megajoules. Mega is how much? Is times 10 to the power of 6 of electrical energy drawn from 240 volts main supply for 24-hour period. Okay, what is the average rate of electric charge? Q over T, right? Rate is basically over time. Electric charge is Q, right? So Q over T here, I'm supposed to find the charge first, right? In order to find the charge, I'll need Q is equals to IT, right? So I don't think I have I here, right? I have I have E, I have V, I have T. Oh, I can use the E equals to VIT formula. Then I would have been equals to E over VT, which is going to be 200 times 10 to the power of 6 divided by 240 divided by the time. In this case here, since it is in hour, I will just keep it in hour. So it's going to be like 200 times 10 to the power of 6 divided by 240 divided by 24. Then after that, this answer here, I'm supposed to divide it by 24 as well, which is going to be wrong. Oh, and times with 24. Oh, yeah, okay, sorry. This answer here, I'm supposed to get 347.22, right, as my I. Then this 347.22, I'm supposed to times the time, which is 24. Then this answer here, I'm supposed to substitute it back here, and then divide back with 24. So it's going to be like 34722 times 24 divided by 24. So I cut it off. So it will actually give me a total answer of somewhere around 35 kilocoulombs per hour. Right? Yeah. Yeah, probably might be a bit confusing for some of you guys, but let me repeat this again. All right. So looking at this information here, first and foremost, I have E, I have V, I have T, right? And if they want me to find the average rate of electric charge, is basically Q over T ma. That's why you can see it's coulomb over hour. In order to find Q over T, first and foremost, if I want to find Q, Q's formula is IT, right? And from here, I only have T, I don't have I. So I have to use the E equals to VIT formula. I would have been equals to E over VT. In this case here will be 200 times 10 to the power of 6 divided by 240 times with my 24. The reason I don't change this into seconds is because the answer is in hours, so it doesn't really matter. If I press this into my calculator, I'll get a final answer of 3472222 amperes, right? This 34722 amperes can be substituted into here, which is going to give me like 34722 times with the time, which is 24, right? Which will, in this case here, will be 34722 times 24 will be 833,328. Then this is going to be my Q, right? Which I'm supposed to substitute into here. 833,328. I'm supposed to divide by the time, which is yet again 24. Divide it back to 24 here, and you will yet again arrive back to the same value of 7222, which is, in other words, 35,000 coulombs per hour, which is supposed to be C in this case here. Okay, so yeah, I'm supposed to do it one by one, and you should be able to find the answer in this case here. Right. And finally, moving on to paper 4, a cylindrical metal wire W of length L and cross-sectional area A has a resistance of 16 ohm. A cylindrical metal wire that has a length of L and a cross-sectional A has a total of 16 ohms. The second cylindrical wire, which is half the length, it's half the length but double the area, half the length but double the area here, double the area but half the length, is made of the same material. Determine the resistance of wire W2. Now first and foremost, you can do it one by one, comparing the length. When you double down the length, you actually become 8 ohms only, right? But when you double up the resistance, you double down the when you double up the area here, you're going to double down the resistance, because the formula is resistance is equals to length over area, right? This one decrease, then resistance decrease. This one increase, the resistance will decrease as well. So comparing the A with 2A here, it it doubled up in area, right? So I'm going to double down the resistance again, which will ultimately become 4 ohm here. So my answer is obviously supposed to be 4 ohms, okay? Just by doing simple comparisons. The effective resistance of W1 and W2 when connected in parallel, which is 1/16 plus 1/4, right? Which is going to give you 5/16. This is not your final answer because this is only RT. RT would have been 16/5, which will be 3.2 ohms in this case here. It's supposed to be 3.2 ohms. The parallel pair of resistors in B2 is connected to a battery that is made from 3 cells in series. Each cell is E here. There is a current in the resistor. State the EMF of the battery. If it's 3 cells and each of them is E, then obviously it's going to be 3E as your answer lah, this one. Right. Then the current in the battery IB and current in W is I1. The current in W2 is I2. Pick a tick on one box to indicate how this tree is going to be. So obviously the current in the battery is going to be the largest lah, right? Because it has to split to these two ma. And since W2 is 4 ohms, it means to say the current here must be larger than the 16 ohm ma, right? So it's supposed to be IB to I2 to I1. It's supposed to be IB to I2 to I1 here. It's going to be this one here. Okay? Then moving on to the next part. Figure 8.1 shows a circuit that contains a battery of electromotive force 6 volts. It's 6 volts here. An ammeter and a 20 ohm resistor here. State the name of component X. This is obviously supposed to be a variable resistor, guys. It's supposed to be a variable resistor. The potential difference across the 20 ohm is measured with a voltmeter. On figure 8.1, draw the symbol of the voltmeter in the circuit. So obviously you can draw it here lah, right? It's supposed to be either on top or at the bottom, but as long as they are parallel, it is definitely acceptable already. Then the potential difference across the 20 ohm resistor is varied from 0 to 6. For each potential difference, the corresponding current is measured. On figure 8.2, draw a line to indicate how the current measured by the ammeter depends across the 20 ohm resistor here. So if I look at this graph here, I have 0, 1, 2, 3, 4, 5, 6 volts, right? So if I have the resistance, very straightforward lah, I can use the I is equals to V over R formula, which is Ohm's law, right? And I can just use a constant of 20 and I substitute 0 in, which is obviously going to be 0 amperes and 0 current, right? Then I substitute 1 in. 1 divided by 20 will be how much? 1 divided by 20 will be 0.05. So 0.05 will be somewhere around here lah, the middle, right? Then it's supposed to be 2 divided by 10, which is obviously going to be 0.1. Then it's 2 divided by 20, which is going to be 0.1. Then it's going to be 3 divided by 20, 3 divided by 20, which is 0.15 here, right? Then 4 divided by 20, which is obviously going to be 0.2. Then 5 divided by 20, which is going to be 0.25 here. Then 6 divided by 20, which is going to be somewhere around 0.3 here. From here, all I need to do is just draw one straight line, which is in tally with Ohm's law, right? This is obviously an ohmic conductor with constant resistance. It should be a straight line in a voltage versus current graph or a current versus voltage graph here, right? Then a second resistor is connected in the circuit parallel to the 20 ohm. State how the combined resistance of the two resistors in parallel compares with the resistance of its own. Whenever you connect anything in parallel, the resistance is going to decrease, because anything connected in parallel will have less resistance. The potential difference across the two parallel resistors is changed and the current in the battery for each value is measured. The second line could be drawn on figure 8.2 to indicate how the current measured by the ammeter depends across the two resistors in parallel. State how the second line differs from the origin. You are not expected to draw the second line. So first things first is we know for a fact that the second line is going to be less, the second arrangement is going to have less resistance, right? And if it has less resistance, then obviously it should tilt more towards the I graph, the I part lah, right? Because if you tilt towards here, it means to say the resistance is greater. If you tilt towards here, it means to say that the resistance is less, because if I use the resistance equals to V over I formula, increase in this is going to increase this, which is going to be this line here. That's not what I want. I know that I have lower resistance, right? So I need to increase current so that this is going to be this, right? So it's supposed to have a steeper line, guys, right? The line will be steeper than the first one. Okay, or just write greater gradient or anything that's logical, that is definitely acceptable as well. Look at the final question here. Figure 9.1 shows a circuit that includes a battery and EMF of 12 volts. The reading on the ammeter is 0.15 amperes. Calculate the resistance in the circuit. 0.15. So if it's 0.15 here, first and foremost I need to find the voltage. V is equals to IR. 0.15 times 20, 0.15 times 20 is supposed to give me 3 volts only. And this here is supposed to have the remaining of the 12 volts, which is 9 volts, right? So with the current in the series is supposed to be 0.15 amperes as well. So if I want to find the resistance here, it's going to be 9 divided by 0.15, right? Which is supposed to be 60 ohms. Right, combine these two together is obviously supposed to give me a total of 80 ohms here. Okay, and that's how you're supposed to do 4.3.